Hello, everyone. Good evening. I'm glad to meet you again this week. And it's been like exciting few set of weeks. And this will be like this will be the final lectures for this fellowship officially, based on the following session will be much more like one-on-one meetings to talk about your project. So in this project, we are just going to touch like a bit of like key things or key ideas of how you can replicate PyTorch papers or experiments and how you can run them on your own at the end of the day. So overall, what we've looked like end to end, how you can start with PyTorch itself, how you can manipulate tensors, and how you can build and train computer vision models that could, to some extent, we could say intelligent to do some form of prediction for you. So let's say you have some really new exciting work, maybe, I don't know, by OpenAI or DeepMind. So how can you replicate something similar? But here we're going to look at very small scale works and see what you can do. And we won't really go too deep into the details of the paper. So a bit high level so that you get the general sense of what we want to do, inshallah. So yeah, so as always, we just use this. Yes. So with in general, you see like there's like lots of body of works over like the years. Like always, you find people publishing new paper upon new paper upon new paper, especially in AI. So AI is like one of the most trendiest topics or areas in general. So, but I think one issue is like people do report or do talk about like the results they've gotten. So there are like a number of things you could do from that. So one thing you could do is either you maybe appreciate their results on if you are like a scientist or hope to be a scientist or a deep learning engineer, you want to like experiment and kind of dig deep. What did they do exactly and how you could do something similar. So which leads us to paper replicating. So you read a paper, how can you perform something similar? So that's one. So in this particular work, we'll just look at what we call VIT, Vision in Transformer. So don't worry if you don't have any idea about Transformer, we'll just talk about it like very briefly. Then we'll talk about how you can use these transformers for vision. So, and just a few things like why should you like kind of replicate papers? So after like someone has published the work, maybe your colleague or a very top company or some very big research lab. So why do you want to replicate their own work? So one important thing you want to do to replicate their own work is for your personal learning. How can you like make use of the technologies they've used, or what can you learn? Because most times it's by doing, you get to learn better. So you can read a paper, you can understand, but when you don't do it or when you don't practicalize it, so everything like easily fades away, then it's easy to get lost in the details, except if you start experimenting with this, then you know actually what they did and it can help you like broaden your thinking at the end of the day. So one other thing is you could help to verify some experiments that have been done previously. So among the why is maybe you can use it for your personal learning. Then you could like verify some maybe experiments and results. So because like people publish a lot and they kind of tell you like they've gotten this XYZ result. So to like kind of make sure the claim is true, then you want to also run it, like you replicate their experiments, you take their hyperparameters, which we'll see, and try to do it over and over again. Then you can see how things work underneath, or if they actually claim what they do, they claim like what they did, it's actually doing what it's supposed to do. Then finally, you would want to maybe do some open sourcing work. So the open sourcing work, which yeah, right now maybe so open sourcing work making your work available to others. Maybe they've published this really cool paper, but there's no code available. So which is like typical of the case. Let's say you are looking at like OpenAI and you want to like open source, maybe build that technology so that general public can use, then you could like replicate a paper, write the code, then just publish it somewhere, maybe on Hugging Face or on your GitHub code, like you've been doing already with some of the courseworks, and anyone can come see what is happening underneath and really appreciate your work and effort for doing those. So that's like some key reasons for replicating machine learning papers. So right now I'll just like run very fast on it. This like with like our previous work, so you can go through the notebook by yourself and see what's been done. And at the end of the day, but here is just to like make the ideas much more clearer to you. So I will just keep a few things in general. So the paper that we'll be trying to replicate today is like Vision and Transformer. So which is very popular paper, VIT. I think that's about some maybe 5 to 8 years ago. So mostly by like some Google researchers, they were in Google, but they've all spread around the world. So I will just keep a bit, but don't worry about Transformer if you have no idea. So, but we'll still talk about it in details very soon. So as always, you remember like our machine learning pipeline, how it starts always. So as we said previously, and I'll also say it again, so every problem has this kind of general pipeline. So just a bit of few things will change within the pipeline. First, it starts with your data, then you have your model, then you do maybe some evaluations at the end of the day. So this can be your evaluations to help you fine tune the model or make the model better. But this is like one of the general pipelines. So it always starts with data, then your model, then you do some evaluation or get some results at the end of the day. So one key thing, as you mentioned, is like data is very important. For a model to perform well, you must have like really good data. So for this, we are continuing using like the data set that we have, like with PISA and stick, and you do some classification. You have 3 classes, and you do some classification based on that. So like we said also previously, you have model, and one of the key things our model is the architecture of the model. So it's like, just think about like the brain, and how is the brain structured in this instance? So maybe the brain of humans and maybe those of other, maybe animals are a bit different. So maybe the architecture helps it to learn better. So in this particular model, you see it has a different architecture compared to the one you've been seeing previously, which we'll also talk about. So yeah, so this is like the main thing. So for the data, we've already looked at a few things. So it's similar data, similar things happening underneath. So I'll just, for the sake of time, then briefly skip into it. So most times you see they talk about like VIT or VIT paper. So what it generally means is vision transformer. So, but don't worry, we'll get into it so that you get to understand and appreciate like the architecture of the model at the end of the day. So yes. So like always, you will, okay, let me try to run this. Wait a minute. Um, yeah, so if you have any questions, please feel free to ask. Yes, Mariam, oops, your hand is raised.
Yeah, I've dropped the
Ah,
message.
okay.
Okay.
Yes, so there is a question for Mariam. Mariam, is there any reward for replicating or making it available to public? And does it mean it can go into CV? Yes, thank you so much for the question. Yes, I think you have like really good advantage if you publish open source work. I think you are very much recognized like with distance. I think one is your public visibility. People get to know you in the like deep learning world. So they know like XYZ person has replicated this experiment. Let's go check out our code. You get like public stars or you get like stars on your repository. So I think apart from it strengthening your skills, since you've practiced, you've gone through like the hurdle of open sourcing the work. So if you have like, let's say you're applying for a job in this case, so you can easily put it in your CV also. So it's like a very massive, it can be like a mini project that you worked on. So if a recruiter comes, he wants to see what you have in store. So he would maybe ideally look at your CV, then they'll see, yes, this person has done like this project. They have open source VIT, which maybe no one has done or very few people have attempted to. And the result is comparable to the original results from the paper. Yeah, they'll say, this person has like really good technical skills. Like they could understand the paper itself and see how they can transform the ideas from the paper into the like something practical that people can use. So it's like it's a very, very valuable skills to use. And at the end of the day, during your interview, they'll ask you to discuss a project you've worked on. So even if it's like just open sourcing some particular work, and probably it's the kind of project or some paper that has not been like open source quite frequently. So it's a big plus for you. So you can like talk in details about the paper and like your challenges you face and how you overcome it. So it's a big talking point in interviews also. Yes. Thank you for the question. Yes. So yes, so like always, when you want to start your project, let me see. So you just do some installation and some importation of your PyTorch library. So we've been doing a lot of that previously, so we won't waste much time. So I think for the sake of time, I'll just run everything. So, but I'll explain to you in details, don't worry much. So here you want to get the data. This was the data set we've been using all along. So that's the pizza, stick, and sushi data sets we want to classify. So we want to like download it, then we load it, then transform it into data sets. So we've seen that already. Then, but one key thing is because now we want to like replicate experiments. So since you want to replicate experiments, you want to make sure like everything that was been done in the experiment tallies with what you want to do in your own experiment. So imagine someone gives you a recipe for making egusi and you want to replicate that. So as much as possible, we want to like measure the same amount of cups of egusi or the same amount of like Maggi or ingredients you've used for that recipe that person used in your own recipe so that you replicate it exactly before. So in the paper, you will kind of see, so I'll jump a few things, but feel free to like bring me back. And so you kind of see in the paper, what they use is, you have an image of here that has this height and width. So in the paper, what they use is 224 by 224 in the paper. So we also want to adopt that, which is like the training resolution. And they use a batch size of this 4096. So if you remember, the batch size just means like in each iteration, how many images it will see in one go. So initially, before now, we've been using the batch size of 32, but you can see this is much bigger. This is like 409. So this is like very massive. This is like more than maybe 1,000 times the initial batch size we're using. But this becomes a challenge. So because the current hardware likely you'll be using, if you're using like the hardware here from Colab, maybe you just have some T4, which has maybe, let's see, 40 GPU 40 gigabyte of GPU memory. So you can't fit this like you can't fit this of the original experiment into your GPU. So because it's too big. So you need like really massive memory in that regard. I don't know if you get it. So in our previous experiment, we used to use like 32 images. So imagine we want to train a model. Let's say we have this model we want to train. And definitely like a data will come into the model and the model will learn from that data and it makes some prediction. So initially, what we do is feed this data into the model. But there's a limit in which, because your hardware needs the capacity, your hardware has like some gigabyte of memory. So first, your model is on your GPU, and now you're feeding the data into the GPU so that you can compute. So everything here is, let's say, on your GPU. So because it's faster for computation. But let's say I increase this data by a lot. Let me see, maybe times maybe 1,000. It becomes too big for the GPU to handle at the same point in time. So you will have to like manage what you have or manage based on what you have. So you cut your cloth according to your size or something like that. So we don't have sufficient GPU. So right now we'll just stick to 32 based on the hardware we have available. So that's it. So as always, where we have this image size. So based on the paper, they use 224. We want to use the same image, the same size. So what we do, remember our compose here is just a pipeline. So we are telling that any image that comes, it should go through this pipeline. So first we want to resize, then maybe just transform to a tensor so that it's like a PyTorch tensor at the end of the day. So this resize here, it will transform it to 224 by 224. So because that was what was used in the actual experiment. So we want to use that also. Yes. So after running, you can see like the transformation that will happen at the end of the day. Yes. So next we load it into our data loader. So like we said, we can't fit like 4K images into the data loader because of the GPU limitation we have. So because you have like an upper limit in the memory you want to use. So we will just continue with like the batch size of 32 over here. So yeah, but if you have like a larger hardware, which hardly is the case, so you can use like much more. So, but you can try maybe 64, batch size of 64 and see can your GPU actually handle it? Then you can keep like increasing as you go on at the end of the day. Yes. But here right now, you just continue with batch size of 32. But this will definitely affect the results. So we shouldn't expect like similar results as the original paper. Yes. And since we're not even using the same data set, so it will be, yeah, not so the same. But if we were experimenting with the same data set and different batch size, so it definitely like affects your results at the end of the day. So this is, so here we are creating our data loader. So we set the batch size to 32, and we've created our data loader, and we have your train and test loader. And yes, so I'll just skip this because this is what we've been working with a lot, and we have like classes already. So we can visualize the image. And so I'll just skip over this and talk more into this. So let me see, just give me 1 minute. Yeah. So here just emphasizes, I'll skip a few things, but I won't miss the necessary details. So I'll expand more subsequently as we go. So here just generally like describes an architecture of a model. So when you think about it, let me just explain. So one of the main building learning blocks of deep learning or machine learning system is a model. So how you architect the model really matters a lot. So at the end of the day, what you might come up with is where you have, so let's say you have this, let me see. Let's say you have, let me say this is your model here. And the assumption is your model will have like a set of layers. So I assume this is like, this might be anything. This might be an MLP. This can be anything completely. So this can be maybe a multi-layer perceptron. This can be LSTM. This can be like anything. So you have layer 1, layer 2, up to maybe layer N at the end of the day. Then at the end of this layer, what you might have is some output or some output predictions here. Maybe it predicts maybe 1 or 0. So what happens, the general terminology, people like, it's just a terminology, but people just see layers. Maybe my model has 10 layers. So what you just do is just to count these layers over here, maybe layer 1 up to layer N. I can see maybe my model has maybe 32 layers. So it's just like generic counting. So there's also like concept of blocks. So I could decide to see, so I could kind of categorize each layer here, maybe layer 1 and 2. Maybe I would say maybe block 1, like maybe this is like block, let's see, block 8. So these blocks are just like a combination of 1 or 2 layers together. So what usually happens is people just use the concept where similar layers or layers that you can reproduce several times. So you just group them into one layer. So assumption is maybe here in this layer here, I might have maybe a CNN layer, maybe let me say CNN layer 3 times. Then instead of me like I can just make this to be one block, and I can store it in a variable, maybe 1 minute, let me just see. So I can say maybe CNN block. So it can just be a variable name, CNN block is called to, then I just create the like PyTorch maybe implementation. I'm just giving some simple notation here, CNN. So I have this. So this has like, this stores like this for me. So instead of me like calling it over and over, so what I just do always is just to call this here. So you just categorize a set of layers together and just name them a block arbitrarily. So it doesn't mean anything. So yeah, so it's just easy for you as a programmer over and over again. So it makes sense easy for you. Yes. But if it's not, if there is anything confusing, feel free to please ask a question and you can unmute at any point in time. Yes. So that's that. So yes. So as you can see here, yes. So you have like a stack of layers and you just call them a block. So how people do them is when you have some layers that are similar to one another, let's say this layer here this set of layers, maybe 1, 2, 3, is similar to 4. It's like a replication. Then you can just categorize them individually as like this is block, and it's easy for you to like program over like subsequently. Yes. So just give me a minute. Yes. So I would like briefly touch into the attention mechanism. So, and then talk about like VIT in attention mechanism, but we won't go too deep, just so that you can understand the general idea about it. So are you familiar with the transformers? Please, you can type yes or no on the chat so that I know how to explain better. Yes. So feel free to chat. Feel free, there's no wrong answers, just so that you know. Are you familiar with like attention or what people call like transformers or something like that? Just feel free. Can you kindly type on the chat? Or have you heard about it somewhere? Yes. Yes. So there are comments coming in. Yes. Okay. Okay, super. Yes. So a few people mostly have heard about it. So one of the key underlying architectures that have been driving like the AI revolution lately, that you've seen, like if you've used ChatGPT, that you've seen that it's really, really impressive and giving you like really good response. It's what they call like the transformer architecture. So yeah. So transformer architecture. So it was like in 2017. And it has kind of gone over several kind of revolutions over the years. So it has changed a lot. So, but this is like one of the most fundamental work that's been done, and people have tried to like manipulate it one way or the other to make it fit or try to build something better. So with transformers, it drives like most of the common things that you see, maybe Gemini. Um, so let me just reshare this again, just in 1 minute. Yes. Yes. So transformers, like 2017. So all the like ChatGPT you are seeing currently, and like Gemini, so they are mostly like based upon this. And you can see it's like a really old work, but it has gone through like several like changes over the years to make it better. So ideally, what powers like the transformers is what they call like the attention mechanism or the attention layer. So I would briefly explain the idea. So initially, how people like build like this kind of models that take in an input, mostly a sentence, is like before like the transformers or the attention mechanism, what they use is, so the main building block of the transformers is what they call like attention. But don't worry, I'll just highlight a bit about it. So what people usually use before now, let's say you have some input, and let's see, I like to play, maybe you put some like dash, dash, dash. You are expecting a response from, it can be a model or anything. So what you can do is you can represent this as what we call tokens. It's just that it represents like some characters, but let's take this as a simple representation of this input. So you can see here you have token 1, token 2, and maybe let's say T3, T4. Let me see some, just give me a minute. What? Yeah, so I think this will be better. Yes. So usually what happens is, let's say you have a model and you want that model to do some form of prediction for you. let's say this is your model and you want to pass it any input. And ideally it should be, maybe let's take text for instance, and it should also produce some maybe text for you. So what you have to do, first you have to like tokenize. So it's like yeah, sorry about that. So what you want to do first is like tokenize your text. Let's say we have a text saying maybe I love playing games. Like Ibrahim, please can you, I think is it? No, I don't think it's Ibrahim. Yeah. Okay, thank you very much. Yeah, so let's say you have this, like I love to play games. So what you can do is represent this as tokens, but don't worry too much about this. So just each word is an input for, or an input for simplification. You have like T1. Let's say you have T2, T3, or maybe T4, and perhaps T5. So we want to pass this into our model so that it can be able to predict maybe the next word. So ideally, what you want to do is to predict anything for you. So here, we want to charge you with the task of predicting the next thing. Let's say I give the model a text, I love to play games like, so it should be able to predict something reasonable, something that it's good at the end of the day. So what usually happens before like attention mechanism? So you have these models like let's see, RNN, LSTM, and the rest. So how it happens with this RNN and LSTM? So you have their network. Let's see, you have this network. Let's see, RNN in this instance. So what happens with RNN? First, you pass it the first input. Maybe let's see, maybe it goes to the model, then it performs some maybe computation. Then next, maybe step 1. Then step 2, you pass it maybe love. Then it also like maybe goes to the model, then playing. That's like step 3. Then it also like goes to the model like that. So it's like one input after a time, one input after the time. Then after a while, then the model maybe does some prediction at the end of the day. Maybe games like, let's say, Need for Speed, something like this. So it's good. It worked then, but it wasn't as efficient or as we wanted it to be. Then one improvement came in, which is to use like the attention mechanism. So instead of having these inputs coming one after the other into the model, so why not we take the input as a whole? So that we can see what is the relationship between the model itself, between like the tokens itself. So what attention mechanism aimed to do was, instead of having this like serial input where you have I going in, then love going in and the rest. So why not all everything goes into the model at once? Let's say this is our model, and you can have so everything will just go at once. So what happens internally in the model? So it tries to learn what is the representation between each of this. What's the representation between I and love? What's the representation between love and playing? So it kind of tries to see what is the dependency between each one of this. So how does I relate to love? How does I relate to each of this? And how does like love? So each of the token have some relationship between them. So that's where like the name attention comes in, because each token or each word here is attending to each of the other words in the sequence. So that's where like the general name of attention comes in, like it's attending to each token is attending to one another. So you can see like love and playing or love and games. So they might have some kind of relationship between both of them. So you might have like some scoring system in which tells you like, since you love something or playing games, so it means something positive. Then it tries to search between it's maybe let's say knowledge base for simplicity. So how does it relate love and playing or love and games? Then what can it predict next after that? So that's where this models generally become better and better at the end of the day, because it's seeing the relationship between one another and to be able to predict well. So compared to like the previous models that use like RNN or LSTMs, which sees each input as single as its own. So without doing like some computation at the end of the day. So that's where like the name comes in, like attention, because each token or each word here is attending to another token in the sequence. So that's the general idea. So for it to attend to one another, so they have what they call, let's see. So they have what they call, so I will need to go up a bit. Just this key, query, and value. So Q here, it means query. Don't, I'll give you a very simple analogy on this. Then K here is called key. Then V here is called value. So what happens is when you have like a question, so or any input to the model, so that's what you call query. So here, let's see, I have maybe a question, or if you are familiar to using like ChatGPT, you can say maybe a prompt. So I can say this is, here is my query here. So let's say I ask a question, maybe tell me about, maybe I have this prompt here, maybe tell me about Napoleon or something. So this is a query or this is a question to the model. So what the model does is think about like this key here as, let's assume you're in the library and maybe trying to read a book or trying to find out more about Napoleon. So with this query, so you can easily like check. Ideally, you don't want to go through all the books in the library because you don't have like that valuable time and you want that information as quick as possible. Then think about this key here as the title of books. So because it's easy to look at like the title of books in the library, so you can easily search Napoleon and you can see like books that relate to Napoleon or much more easier in some way. So if you have like title of books or books that have Napoleon, it's easy to like just dig into them and find the information you need. So after you've gotten like a title of books, your query here, from your query, you can go to search the keys. And when you have like valuable keys and you can simply get the books that relates to books related to maybe let's say Napoleon in this instance. So what you have here is the value, what you actually want at the end of the day. So that's like the key idea of attention mechanism. You have the query, which is the input to the model. So think about, like we said here, just maybe a question or prompt you give to the model, and you have like key. So key is some kind of value that's easy, some kind of let's say you have some dictionary and keys, maybe let's see the word, and at the end you have like a value, which is the meaning of that word. Or as we said here, this is like the books, the entire books about Napoleon at the end of the day. So this is like just brief intuition about key mechanisms of attention. So hopefully you have better ideas now about it. So, and yeah, so I'll just briefly skip for the sake of time, and the next 15 minutes focus on what were the key ideas in VIT, because it's like a really broad topic or a really broad notebook. So hopefully you get something meaningful out of it. So if you remember before now, what we did is take an image. Let's say we have an image maybe it can be 224 by 224. And what we do is maybe apply some kind of CNN layer into it, and the CNN goes through it. So that worked well then, but I think with what you realize with technology, you always want to improve it. You want something better. Let's say you have 80% accuracy, you find ways to get 90% accuracy, 100% accuracy. Then for other tasks, you try to improve as much as possible. Then instead of using convolutional neural network, so what they did, they kind of asked the question, can they use transformers and vision? Because before now, transformers were majorly used in sequential language modeling. So tasks that relates to like text. So people try saying like, since it worked well for text, can we like take some bit of like transformer, the attention mechanism, and put it into vision? So that's where the ideas of vision in transformers comes in. So I will just briefly explain this, then we'll look at the code, then we'll see how things work here. So as we said, just give me a moment. So let's say we're still working. Yeah. So I'll explain the main idea. So hopefully when you read it on your own, you'll understand it much more better. Let's say you have an image. Let's say 24 by 24, and you can have maybe pixels. Yeah. So each square here is a representation of a pixel. So instead of applying CNN to it, here I want to apply a transformer into it. So one of the first key things we want to do is create patches from this image. So everything here, this dot here is a pixel. So as you know, pixel is the smallest representation of an image. So you can think about the screen you're looking at now. So if you notice, if it's not too fine grained, you can see like a few dots. So those small dots are pixels. So one of the first things we want to do is create patches. Let's say we have image. So patches are much more of like groups of pixels together. So we can create, so to achieve what they did in the paper, so first they create like a patch. So let's say I can group, let me see, maybe 2 by 2 pixels together. I can call this a patch. So I can create more patches. 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 So that is like the very first thing they did. So which you can see here. So you can see you have an image, then you kind of break it down into patches. So what you would do next after breaking it down into patches, you want to flatten it. So by flattening it, let's say at the end of the day, after creating a patch, we can say this patch here is this. And it has maybe, you can say maybe 16 by 16 pixels together. So instead of using this 16 by 16 pixels together, you flatten it. So it becomes a very single sequence of maybe 16 by 16. So that's the flattening that you do. So when you do the flattening, then you have like this. So this is what they call like the linear projection here. So that's like basically like flattening the image. So you remember, so yeah, which is this, and you can see it becomes like this pinkish. So all these pinkish here are like the flattened patches here. But you can see by the left-hand side of this patches here, you can see we have, yeah. Yeah, so these are like the patches that we have. We have each patch. So, but you can see by the left-hand side, you have these numbers here, 1, 2, 3, 4, 5, 6. So what are they? So these numbers are majorly just sequences. So unlike CNN, with CNN, it's easy to know how each pixel relates to one another because you have like a tiny box moving around. So, but in VIT, you don't have that idea. So you want to give it a notion of position. So for each patch that you have, so we can name this patch, maybe patch 1, patch 2, patch 3, patch 4, patch 5. Then you embed this like kind of location into like the data that you have. That's the transformed patch. Then you have this. So each patch, after you flatten it, it has like an index, which is like more of like the position of the patch in the image. And when you have that, then simply each of these, you pass each of the input into like transformer layer that we talked about. So the transformer is basically nothing but the attention block, which you will see or which we'll talk about by the left. So, and at the end of the day, you have an MLP layer, which is like a classifier. Just this is like an MLP, just a fully connected neural network, just so that you can classify from one dimension to the number of classes you have. So let's say you are doing Cypher 10, you have 10 classes, then the output will be 10. Then for this example, you are doing 3 classes, the output will be 3. So just to briefly recap, so first you create patches, which is like some pixels grouped together. Then you flatten those patches. You have like a one dimension. Then with each of the patch, you append it with an index or position embedding, just to have a notion of where that patch is in the image entirely. Then you pass this into the transformer encoder. So transformer encoder is just simply the mechanism, mostly the mechanism we've talked about, where you have query, key, and value. Then finally, you have like an MLP layer just for you to classify at the end of the day. That's this. But don't worry much about the details. So I just to explain the paper, then show you where each part of this is in the code, and we'll call it a day. So hopefully when you run it, then it runs well for you. It's just more of like the concepts of mapping the ideas to the code itself. So you know what is the idea and you know which part of the code it relates to. And most of these are already implemented functions. It's just for you to piece the puzzle together and you have your VIT that you will open source at the end of the day. Yes, so I would just clean this. Then yes. So what is the transformer encoder entirely? So it's just you do. So this is like the transformer encoder here, essentially this, but don't worry too much about the, so things that we mentioned about the key, query, key, and value are here in the multi-head attention. So that's like the major component of with the transformer block. Then if you know that, you know, like almost 80 to 90% of the transformer architecture is just like how these things are stacked together. Then here you have normalization. So since you are from machine learning background, it's more of like, let's say you standardize the inputs coming in, just so that for better training. It's like you minus the mean and divide by the standard deviation. That's normalization, just for stable training. Then next is your multi-head attention, which is essentially the attention mechanism we spoke about briefly. Then you have this residual connection from the input into this, and you add it together. Then you have normalization, and you have like the MLP that was discussed since from lecture 2 and the rest. So this is like just the transformer block. So the key thing here is the multi-head attention, and then the structure of everything together. But don't get too worried about the details for now. So hopefully when you read it again, you would get a better sense of it. So right now, I'll just briefly show you where it is in the code, and just simply just 1 minute, thanks. But please feel free, if you have any questions, happy to answer them on the chat, or you can unmute yourself. So most of these things I've like spoken about it. And like I said, like you already have them, like this layer norm, you already have them in PyTorch. So you don't want to reinvent the wheel by doing it from scratch. You can do it, but you don't want to delay time. And when you do it yourself from scratch, it's not likely it's as efficient as what has been built by PyTorch. So it's just more of, like I said, like putting the pieces of the puzzle together. There's layer norm in the transformer, where's layer norm in PyTorch. I've seen it, then I can put it into my code base. Then much more of like a structuring issue, how you can structure everything together at the end of the day. So I would briefly just show you. Then you have this formula. So essentially these formulas are what were in the pictures there. So I will skip. And hopefully when you look at it clearly, you get an understanding of what to do next at the end of the day. So just to briefly like talk about this. So here, what you have here is like the patch, is the representation of the patch. This major means patch 1, patch 2, patch 3. Then this E here is the transformation. So from where you have like the patch here, maybe let's say 16 by 16 to a linear layer of 16, maybe 1 by 16, something like this. So instead of having it in 2D, you have it in 1D now. So this is where the E comes in. And yes, then you have that. Then this is the multi-head attention. Then this is like the MLP layer, then the layer norm again. Then finally you do your predictions at the end of the, yes. So yeah, each of this is in the code, and hopefully, but don't get too bogged down about the formula. So, but if you have like the general understanding how things work, then I think you will be good to go. So from the formulas, you can see, just give me a minute. Yes. So from the formula, you can see first what you need to do is like create the patches of the image. So how can you create the patches? We know you have this, each image has this shape, and you know like the color of channels is 3 because it's like a colored image with RGB. Then you can define the patch size. So here for the image, they define a patch size of 16. So this is their own, this is a number they develop. So this patch size, as we said here, let's say you have 224 by 224. Then you want to create like patches from this. Then at the end, you might want to do 2 by 2, but here they did like 16 by 16. So for their own easy reason. So perhaps they did some experimentation and they saw like creating a patch size of 16 works better. So they did that. Then you can also extend beyond this and try out other patches and see how it works. Then you can create the total number of patches you can have by using this formula here. That's H times W over, let's say, P square. So you can create what is the total number of patches you have in this, if you create patches from these images. Then you can see using their formula with the value of P, the patch is called 16, you have like 196 patches at the end of the day. So I will just skip this and yeah, so yeah, so I'll just skip this. Yes. So like we said, after, so yes, like we said, so after, yeah. Yeah. So like we said, you have like several patches. So here's just maybe just put the patches together and see what you have at the end. So this is like the patch of the very top or not so top row. You can see from 0 to 16, but here they extended beyond like the entire column of pixels. So just to show where the patch was gotten from at the end of the day. So you can see where it's fully broken down. So each segment of the image has been broken down to 16 by 16, and you can see it numbered. And this numbering is what you will pass in also to your model at the end of the day. So just to explain like the ideas that we had initially, and this is like the full image created into patches, and just for visualization sake at the end of the day. So yeah, so I will just keep this. And yeah, so just these are just some like experiments, but those are like the key ideas that hopefully you get from it. So so here you want to create like the patch embedding. So essentially the patch embedding is how you can transform this like 2D shape of smaller patches into a 1D dimension. And basically you use like some convolution and some kind of flattening as we discussed about. So the convolution is just to learn the representation within that particular patch. And this is like, we can call this a block in your model. So it does just one particular thing at the end of the day. So I would briefly skip this. So I just want to map like the key ideas that's in the paper into like the code itself, just so that you know what's happening underneath. Then finally, or not finally, you have like the class embeddings. So this class embeddings, class token embeddings means like the embedding you have, then you also add like the position, where in space is that image is in the image. So yeah. Then Sorry, I'm skipping a number of things because of time, and I've spent time like explaining the main concept. So hopefully when you look at it, then you get to see how it would be or how things are easily. Yes. Mm, So, so I'm still skipping, but I believe like when you look at it, so just to get you, mm, yes. So I'll briefly like touch into this in a bit. So we talked about like you have the transformer architecture. So first your input goes into the layer normalization. So this is already there for you in PyTorch. So what you just do is like call layer norm, and then you have like the multi-head attention, which has like the key value and query. So it's already like pre-built for you. So the key thing is like knowing where the structure or how to structure it together. Then you can also instantiate it using this. So in general, same idea as we talked about. Then what happens is your input comes in into the layer norm based on the image we have discussed about. Then also it goes to multi-head attention. Then you can see exactly what we talked about. You have like the query, you have the key, then you have like the value itself, which are like basically like the same embeddings, that same input. Then you pass it, then you have an output of your attention mechanism at the end of the day. So just the same key ideas talked about. So this is just like mapping what we discussed and what's supposed to be in the code. But don't worry if you don't understand it. So hopefully when you get to go over the notebook, you have a better understanding about it. So I would majorly sunset here at the end of the day. Then finally you have MLP layers. Oh, skip this. Yeah, it's honestly a lot for a single lecture. So, okay. So finally, you'd have an MLP layer, which will serve as a classifier. So the idea of the classifier is to predict. Yeah, so the idea of the classifier is to predict the final output of your model. Yeah, so you have like number of classes, in which our case is 3 here. So if you, at the end of the day, you are using another different data set, then you can modify this to more than 3. It can be any value of the number of classes. Then yeah, I think that's majorly it for building model. So it might feel like a lot, but I'm sure like when you try to see it step by step and walk through it, you have a better understanding about it. And if you have any questions at the end of the day, just feel free to maybe speak to me on the Discord or any one of the TAs about it. So, and yeah, so hopefully at the end of the day, I think one of the main key learning points for you is at least have an idea of how the transformer architecture work. We didn't really go into the detail, but mostly on the surface, and which also will help you understand how these really big models work. That's like ChatGPT, Gemini, and a number of them. And at the end of the day, you understand what's the importance of replicating experiments. And hopefully you'll be able to do more applications. So maybe when you start out might not be easy, but when you do more and more about it, you get really confident and you can do it like any day, anytime, so no matter how long it will take. So you can easily map out like these ideas into code at the end of the day. So with the notebook, when you try to run it, you will see how it's been built out completely. Then when you have the main thing here is like the model architecture, then everything about training the model is the same as we've done like previous in the last classes. So I would say that's like majorly it for me, but I will, please, if you have any questions, happy to answer them in general. Yes. Yes. So there is a question by Abdullahi. So feel free also if you have any questions, to please send questions. So is it safe to say that the patching and position embedding step replace the initial steps in? Yeah, so there's a question from Abdullahi, whether it's okay to see whether the patching and position embedding replaces like traditional CNN, including like strided convolutions. And just give me 1 minute. So yes, I think the question from Abdullah is whether how like VIT kind of relates to CNN, traditional CNN that we have. So, which is like a very good question. So ideally with CNNs, what you want to do is have an idea of how each pixel relates to every other pixel. So, but when you look at it from a conceptual level, you have like several number of pixels together. So it might not make sense to look at each pixel like individually as it relates to other, which is good, but you are going like really, really low level. But when you look at an image, you can represent an image by, let's say, identifying objects. So those patches might be, you can take them as like mini objects together, even though those might not make sense. So it's more of like having the relationship between patches itself rather than pixels. So we can say that with CNN, it's more of like how each or a set of pixels in a kernel relates to another set of pixels, but it's too, how do I say, too fine-grained in some sense. But with VIT, it takes the advantage of like transformers. So you can chunk in like all the information together and see how it relates. You can have like a pixel at the top left, and you can see how it relates to another pixel at the maybe at the middle or at the bottom right. So you can see these are like far ending pixels. But with CNNs, what happens is like a convolution comes in and it moves around, and at the end of the day, it has like a resulting output, which might likely have a representation, but not fully grasps like the entire representation of the image. So similar to like how we explained with the word example. So with like attention mechanism, you can look at like almost everything at once, like the entire image, try to understand the entire image. Let's say an image, perhaps maybe let's say of me. Let's see here, you can see, let's say here you can see like let's say the board here, then you can see me here. So with VIT, you can look at everything within this particular space and how we relate to each other within my own space. But with CNNs, you maybe start from, I don't know, maybe the top right here, then the convolution starts moving around minimum representation, but the best representation it can make is neighborhoods of pixels within one another. But with VIT, it's easy to look at everything in one go, which is good and cool. Yes. So yes. So hopefully I get to answer your question. And yeah, so I think it's yeah. So if there are no questions, I would say we'll call it a day. Thanks so much for waiting like beyond the timing. So thank you so much. And oh, yes, please, you can unmute. Let me see. 1 minute. I think Ams wants to ask a question. Let me just see if I can unmute you.
Assalamu alaikum.
Wa alaikum salam.
Dr. Hassan da Ogari.
Wala lafiya lau, alhamdulillah. Na gode sosai.
I said some papers are not clear on how to run their models. So in such instances, how can
Yes.
someone try to, for example, I've been trying for almost 2 days to from 10 time LLM. So
Yes.
from the GitHub of the publisher of the paper, I followed the procedure, but I couldn't. So in some situation when from the GitHub repository of the owner of the publisher, he's not clear on the procedure of running the model. How can someone run?
Yeah, I would say it's like really hard, especially if you have like repositories that are not really well structured. So you can take like
Yes.
this, like even weeks to, especially if you have like a different experiment, or if the code base is like structured for the user. Maybe it has like several local parts of the user's machine, then you have to check. And so I would say maybe one of the best way is maybe try to know what challenge you are having. Is it maybe, are you installing a package, or where the specific issue might be on the code? Then I think one thing is, since it's open source, you can email some of the authors. So mostly they are like happy to help at the end most times. So if you have an issue, you can either on the GitHub, you can create an issue on the GitHub page, or rather you can directly email them. Maybe go to the paper, maybe you can check, maybe not the leading author or some corresponding author or any one of the authors, maybe one or two, then email them about like the issue you're having. Most times they'll be happy to respond. So either you go on the GitHub and create an issue, what's the problem you're having on the GitHub repo, or you contact some of the authors of the paper. So maybe some you feel maybe might have some technical, maybe not the professor, or maybe some of the other people that you feel like might have some, maybe one or two. So hopefully it will help you at the end of the day. Yes. So I think they are. So hopefully we'll get to release the groupings of the project by Monday, hopefully, or as soon as possible. Then we'll let you know and the details about the project. Yes. So thanks so much for coming in this weekend, and I hope you do enjoy the rest of your weekend. I'm looking forward to more of the discussion. So officially we are done with the classes, but feel free to ask any questions on Discord. So the next sessions will be, you don't need to attend. So, but you can just attend for question and answer, or if you have a grouping, so, but we'll be here to ask or to be able to answer any of your questions, but will be majorly related to the project we have. So it's a bit free and flexible for you. So if you have anything, you can drop by and ask the question, you and your group. So that will be like the case for the next set of weeks, but we'll outline everything for you to know how it is, inshallah. So yeah, thanks so much for joining, and that's majorly it from my end. Yes. Yeah, you're all welcome. Thank you. Thank you.